ho, ho! Merry Christmas!
Man, the last day of the year, I'm ready to start my vacation. Zach is having his annual Christmas party. I hear he found a structural grade Doug fir. We're going to decorate it with .001 Kip grade 36 steel cubes and try to guess the deflection of each branch. I love that game. All I have to do is review this mix design.
See you next year, Max. Don't forget to lock up.
Hey, at least leave the light on. Actually, these Christmas lights aren't too bad. A little dark, a little creepy. I'm gonna need a miracle to get out of here in time. Who would be here now? Hey, sorry, we're closed for the year. Wait a second. Are you Professor Tyler Lay?
I am. Is this the annual ACI holiday party?
No, that's one floor up. But man, am I glad to see you. Say, do you think you could help me out with something?
Sure. I've got a minute.
Great, follow me. So I got this mix submittal I need to review before I leave. I'm doing it as a favor. I don't even know that much about the project. It's a large custom home somewhere in the Arctic. Just want to make sure I understand everything that goes into a mix design before I just give it the okay.
Sure. What questions do you have?
All right, let's start with concrete strength. This project has tons, and I remember the engineer said something about a lot of it was just kind of minimum strength, and then there was some exterior, high exposure, and I guess what I'm trying to say is, what's the minimum concrete strength I might expect to see here, and what's kind of average?
It's a great question. So you always have to think about what your concrete's going to be used for. If your concrete's internal and it's not going to see the weather, it's not going to be exposed to de-icing salts or freezing, then a good minimum strength is about 3,500 psi. You could probably go down to 3,000, but 3,500 is what I mainly see in the industry. If you're going to have external concrete, you got to really think about how it's going to be used. If it's in the middle of a beautiful, wonderful, warm place like sunny California, Southern California, 3,500 is probably okay. But if you're going to see de-icing salts, freezing weather, et cetera, like the Arctic, 4,000 to 4,500 is where most people are at. And then if you're going to be near the ocean, I don't know if it's near the ocean or not, but some people, that's when you might see 4,500 or 5,000.
How does the higher strength help us in concrete? What does it do for us?
Believe it or not, the strength is not, I talked about strength and weather exposure, but the strength and weather exposure have nothing related to them at all. But strength, people think usually is tied to water to cement ratio. So the way to get stronger concrete, they think you need a lower water to cement ratio. And they're right. And so since there's not a great way to measure water to cement ratio yet, then they use strength as, a surrogate. So they'll specify 5,000 psi concrete when they really want like a 0.40 water to cement ratio. Does that make sense?
Yeah, it does. What do you mean that's not a great way to get a water cement ratio right now?
Well, if you go and look at test methods to measure water to cement ratio, there's very few. There's the slump test, which was developed in 1911, which was great. Duff Abrams, one of my heroes and everything, but that doesn't really tell you anything about water in the concrete at all. I mean, maybe it did back in 1911, but with our aggregates and our SCMs we use now, our fly ash, slag, silica fume, and our admixtures and things, that slump test just isn't adequate. There's a test called the microwave oven test. It's a AASHTO standard test, but it's kind of variable. But I'm actually working on a brand new test that I hope to unleash pretty soon that does measure water content and does give you lots of insights into water cement ratio. But I guess you'll have to stay tuned for that.
All right. While you mentioned that, so the water cement ratio in this mix I'm looking at, it's lower than we specified. What's going on here? Is that okay?
Sure. There's nothing wrong with being lower than what you asked for. It's like having extra chocolate chips, in your cookies or something like that. Or getting an extra cup of coffee. It's just bonus that they're helping you with. So it's not a problem to go lower. Now, it is a problem to go higher, but it's not a problem to go lower. Now, there is a problem with going too low. You might say, well, what does that mean? Whenever your water cement ratio starts to get below about 0.40, you can get something called autogenous shrinkage. Oh my gosh. It just means your concrete can crack even though you didn't do anything to it at all. That's usually mainly a problem in precast concrete or super low water cement ratio concrete. So it's not that common, but just 0.40 is a good bottom basement usually.
Is that akin to a shrinkage crack, or is it its own thing?
Yeah, it looks just like a shrinkage crack, but most shrinkage cracks that people talk about are drying shrinkage cracks. So they're concrete that's been out, that's lost moisture. This is concrete that through the hydration process itself actually is consuming more water than the concrete has. And that causes kind of this internal cracking to occur. And it's a big deal.
What about the high end of concrete? I see some mixes on here that go way up 7,000, 8,000. How high can we go? What becomes unreasonable?
That's a great question too. Usually your strength of your concrete is controlled by the strength of your aggregate. Aggregate makes up about 75% of the volume of concrete. And so if you're going to have to tune your aggregate to whatever strengths you need. Now, there'll be people out there that use 10,000 and higher PSI concrete. When that starts to happen, you start to get very brittle concrete, as in it'll crack a lot easier. And I'm not a big fan of that at all, but I kind of like long-lasting, durable concrete that doesn't crack. Cracks really freak me out. And so those are some of the trade-offs. Now, again, I wouldn't go above. I don't know why you need more. This is going to be a little blasphemous, but I don't know why you need more than about 7,000 PSI concrete. I know that people say, I have to have it because it shrinks my column by 10%. And maybe it does for them. Maybe it's worth it for them. But that actually being brittle in an extreme event like an earthquake or tornado or a hurricane, it just really worries me. And so I try to stay away from super high strength concrete. That's just me.
Yeah, I mean, so when you're looking at high strength, you said it's more aggregate based. When we have different types of concrete, right? 1, 2, 3, whatever. Does the concrete itself, the cement, man, rookie. When the cement, you have different types of cement. Does that affect the concrete strength, or is those types totally independent?
The different types of cement are more about the chemistry of the cement, and it has nothing to do with the strength. It has to do with different properties they're trying to do, like resistant to sulfates or low heat. There is something called a type 3 cement. And a type 3 cement is just a cement that's ground finer than other cements, so it gains strength faster. But it's not necessarily stronger. Water to cement ratio and the strength of your aggregate are the two things that dictate the strength of your concrete.
So type 3 is like the instant coffee of cement.
That's right. And there's always some drawbacks from going to instant coffee. You know how that works, right?
So aggregate. In this project that we're looking at here, he's got, all sorts of weird aggregate sizes. I think it's hard to get aggregate up there. Is 3/4 just the standard? That's what I tend to see most, but I know we can go much lower and way, way higher. When would we use this range?
So there's a lot of different people that have a different ideas about this. Let me just try to make it my view. So 3/4 inch size aggregate is most commonly used is because we want to sell one product, that one aggregate source in a sense, that can be used in a ton of different mixtures. And what commonly controls this is rebar spacing. So if your rebar gets too close together, your aggregate will bridge and you won't get good concrete around it. If you don't get good concrete around it, it doesn't bond to your rebar well, and concrete doesn't do that well when the concrete is not bonded to the steel that's inside of it. So if you have about a 3-inch spacing between bars, a 3/4 inch to a 1 inch maximum nominal size aggregate will fit that, because it's usually 3 times your aggregate size. Mm-hmm. And so that's why it's most commonly used, because a good bar spacing is about 3 inches or so. Now, you'll use different size aggregates, because if your bar spacing is closer than that, then you're going to need smaller aggregate. And sometimes you'll use bigger aggregate because there's this idea out there, this concept that if I use larger size aggregate, then I need less cement. But I'll tell you, it's not right. It's not right at all. It has to do with your aggregate gradation, your aggregate distribution. And if you want to learn more about that, you can look up some stuff called like optimized aggregate gradation or tarantula curve. And it's a way to look at the aggregate gradation and get an insight or prediction on how that impacts the workability or how much paste you need. So I've said, giving you a lot of information there to say that sometimes using larger size aggregate can help you in certain applications.
Well, then here's one for you. On this project, they've got this weird horse stable kind of next to a runway. I'm not sure what it's about, but the mix for the runway uses a really large aggregate. Is there a benefit to that, or is this just taking up space and using less cement, like you said?
So there's this theory that has been around a long time that if I use larger size aggregate, that I need less paste. Paste is your binder, your cement, your fly ash, your slag, and water. Now, so again, the thought is that if I have less surface area in my mix, then I need less paste to coat the surface of my aggregates. I'll tell you what, though, that's not right. Okay, people used to think that was right, but it's not right. Much more research and data has shown that it's more about the aggregate gradation that matters. So the size distribution, the packing of the aggregates. Now, it is true that if you use a larger size aggregate, you have the potential of having a better packing or a better gradation. Okay, so there's some truth to the old wives' tale, but it's not like the gospel. Okay, understanding the aggregate distribution is what matters, and there's optimized aggregate gradation. If you want to learn more about that, tools about that, and one of them, my favorite one, is the tarantula curve. It tells you about aggregate packing and aggregate actual distribution and how that ties to paste content. So I think that's a better approach to just always calling out a larger stone or a smaller stone or something like that. It's to better understand the science, because that's that larger stone concept is like from the 60s, okay? And we know much better. And you might say, well, why haven't our code changed? Or why hasn't the code changed? Well, we're working on it, okay? It's coming. ACI documents are being voted on and thought about, but change takes some time.
I feel like we don't often see the gradation when we get a mixed design. And if we do see the gradation, I don't know that I would be able to say, hey, mixed designer, or concrete supplier, please tweak that a little bit, because they have the test results, already for some mix that they put together a long time ago. Do you think there is a place that we could say, like, I would prefer if the gradation was closer to this, or are they just following an ACI standard?
Yeah, so if I'll be really honest with you, most aggregate producers and concrete producers are doing the best they can, and they're using something that they know that works because they've used it in the past. Yep. And there are times, though, when you want to reduce paste. I mean, it can help you reduce cost. It can help you improve durability. It can help you improve sustainability. And in those times, you need to pay a little bit closer attention to the aggregate gradation. So I think the tarantula curve, and I'm biased because I developed the tarantula curve, okay? But I think the tarantula curve does a really good job of helping give more information. And so what I would recommend you do is that you require that they plot their aggregate distribution results on the tarantula curve. And you wouldn't be the only one that would do it, all right? Mm-hmm. There's many state DOTs that require this right now. Minnesota is one of them. New York is one of them. Wisconsin is one of them. Texas, Oklahoma does it. There's many states out there that are doing it, all right? And there actually, some specifications require you to be inside the tarantula curve. Now, I'm not saying you should do that, all right? Because you have to really think about what it is you want that mix to do, right? You don't always need like the creme de la creme of mixed designs, all right? But there are times out there when you do. And when you do, it's a very simple tool to help you with that. Now, we're augmenting the tarantula curve and making it better all the time, adding new tools to it, and I hope to talk more about it publicly soon, but we've got some really cool things that are going to make this even easier for people to do in the future. But short term, that's what I would do. Mm-hmm. If I was an engineer or if I was an owner, I would just put it in my spec that you shall plot your mixtures as per the tarantula curve, and I'm happy to share a bunch of examples of specifications where people have done that. All right. Perfect. And you can just use that language, and then you get a number, and it's really easy. if there's like 3 checks, and if you meet all 3 checks, things are great. And if you don't, then you're going to need more paste. I didn't say you couldn't use the mix. I'm just going to say it's going to be more costly. It's going to be less sustainable. It may be less durable. And if that's important to you, then that's a reason to pay attention to that. Does that help?
Absolutely. Next question is somehow related to aggregate size, and I don't actually know how. We're looking at air entrainment. So if you're looking at table 19331 in ACI, the target air content is related to the aggregate size. What does the air do for us in there, and why are they related?
So first of all, we add air to concrete for freeze-thaw durability. That's number one. And we also add air to concrete because you can sell people air. I mean, how cool is that?
Yeah.
You can sell people air that they whip, inside their concrete, right? And there's actually plenty of food products out there that are not low fat. They're kind of like in the middle fat. You know what I'm talking about, right? Like yogurt's very, 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 very popular like this. And also ice cream. All they're doing is whipping air into that stuff, all right? So we do it inside the concrete world as well. But air is good if you have freeze-thaw problems. Air is good. If your concrete gets wet and it freezes, and the Arctic is definitely one of those places, then you should air entrain your concrete. Now, you asked another question. You said, why is the air content related to the aggregate size? I'll tell you, the air content has nothing to do with the aggregate size. And you might say, well, then why is it in the table? You remember that answer I gave you before about how people used to think that aggregate size was tied to paste content? I was telling you about that, about larger size aggregates for runways or whatever. Yeah. Can't wait to see this runway in the Arctic, man. Maybe it's for reindeer? I don't know. Anyway, so they used to think that aggregate size was about paste content. So they used to think that if I had a larger size aggregate, that I could use a lower size paste content or lower paste content. And since my air protects my paste, then theoretically I need less air if I have less paste. You follow me?
Yeah.
But that's not necessarily right. Because just because I have a 3-inch size aggregate or even a 1.5-inch size aggregate, I have to know how much paste is in my mix. And we don't usually pay attention to that. As engineers, we usually just trust the table and we think that, they're all related. But I'll tell you, they're not. They're not at all. So what I would recommend is that you require about 6% air inside your concrete. And I wouldn't worry at all about aggregate size. Okay? And you might say, some smart people out there might say, whoa. Shouldn't I require my air content based on my paste content? Sure, you could. But now you have to know how much paste is going to be in the mix. And when you specify a job, you don't even know what the mix design is going to look like. So my recommendation is 6% air. That's what you require, right? And if you're really worried about freeze thaw, maybe you ask for 7% air, right? And I wouldn't worry about it. And we could get into more details if you want about bubble size distribution and bubble size spacing, but it's kind of nerd talk.
Hey, that's all right. We like that stuff around here. But I got a question for you. I've always wondered this. How much air would be in concrete if we didn't add any more? Just the natural condition.
Yeah, when you just make concrete, you trap air inside of it. And it's called entrapped air. And it's usually around 2%. But it depends a little bit on your aggregate distribution, really your sand content, and the size of your sand. But about 2%.
All right, so we got other things in here besides cement and aggregate, some admixtures. We got some pozzolanic material or something like a cementitious admixture. What is this stuff? It says it can be up to 20%. Why 20%? What are we looking at here?
I think you're talking about fly ash. So let's back up though. There's all kinds of different, we call them supplementary cementitious materials or SCMs. There's slags that can be used up to about 50%, 40 to 50%. There's silica fume, which is usually used at about 5%. And then there's fly ash, which is usually used between 20% and 30%. Now, those are the most common ones. There's some other weirder ones out there like natural pozzolans, which is like volcanic ash, calcine clays, which are clay that you dig up and you burn, and ground up glass. That's a new popular one. I don't know about popular, but that's a new one that people are talking about, chatting about, things like that. These are waste products. You're like, waste products? I don't want to put waste products in my concrete. No. This is great. This stuff makes your concrete better. It makes it more durable. It can make it stronger. It can make it more workable. It definitely makes it more sustainable. And it definitely makes it more economical. So there's a ton of benefits of these materials. But you ask me, why are they limited? Why can't we use infinite amount? Well, these recommendations, 20% for fly ash, for example, are a good recommendation where you can use the material and you don't commonly have lots of problems. But that doesn't always mean that 20% is the number, because you could do more testing and you could find out 30% works great, or 40%, or 50%. And actually, I think the future of concrete, maybe not for this one, but the future of concrete is going to be a lot more SCMs, because people are going to be interested a lot more in sustainability in the future. And the only way to improve, or the biggest way to improve the sustainability of your concrete, is to reduce the amount of clinker or the amount of cement that's inside your actual concrete mixture. And they're going to be looking to SCMs to do that in the future.
Interesting. That's really cool to hear about glass as an SCM. I had not heard that, and that is just like really neat. Glass is a very poorly recycled item. It just doesn't work very well from what I've read about it. So I know, this place does have some sort of toy plant, and I think they manufacture a lot of stuff. So they might just be taking some of those byproducts from there. I've heard some people mention that as we are decommissioning coal and changing the way we manufacture things, some of these byproducts are going to be less common. Which of the ones you mentioned do you think are going to be around a while, or is that true that some are kind of going away?
I think everything's in flux, just like every single day. A lot of things are becoming more expensive. A lot of things are getting hard to get. So slag is a waste product from producing steel, and it depends where you're at in the world. But if you don't have a steel plant that's close, or if you're not near a port where you can bring in slag from overseas, then slag is probably extremely rare. So you may or may not have it. Coal-fired power plants are going away. And so a lot of people think that fly ash is going to be going away. Well, I would say fly ash as we know it is going away, but reclaimed ash, this is material that's been fly ash in the past, that's been sitting in ponds. Oh, baby, it is good stuff. Okay, we have got a project now where we've tested 14 different sources. We're actually writing specifications for people to use this material. This material is already being used commercially inside the United States in 4 different states now, about to be about 10. And so I think you're going to see a lot of these like reclaimed fly ashes kind of save the day and like appear. Now, how long is it going to take for them to save the day or show up, though? I don't know the answer to that. All right. It's going to depend locally on how bad you want it and how much you have it. But I think things are going to step in. I think there's always going to be a way to step in because durability is so essential to concrete. In certain applications, you just have to have it. And you're going to pay whatever it is to get it because people don't like to replace their concrete every 20 years or so. They want to shoot for 60 to 80 to 100. And for certain applications, that's worth it. For other ones, inside of a building, maybe those are going to go away. Maybe we're not going to use ash there or slag there or anything else there. But these other SCMs I talked about, natural pozzolans and glass, that's one reason why they're becoming much more popular is because people are looking for alternate local solutions to make the best concrete they can.
Okay, so I think that's most of the mixed components of the submittal I'm looking at. The last couple pages here are all just a bunch of testing values. I'm seeing a couple of weird things. So one mixes here only has a couple of test breaks. How many do I need to see to say that this mix is okay?
Interesting question. So it really depends on the size of your sample. So if you're doing cylinders, which most folks that hear this maybe are, if they're 4x8 cylinders, you're supposed to have 3 of them. If they're 6x12 cylinders, you're supposed to have at least 2. That's for a single measurement. A single measurement a single day. And you can have more than that, but that's kind of the minimum that you're shooting for. Sometimes they'll try to get away with 2 cylinders for the 4x8s, but you're really supposed to have 3. Does that answer your question?
Yeah, I think it does. I mean, another thing, so this is from the Concrete Mix guys. They, I guess, have tested these cylinders to prove that this mix is adequate. So we have a couple on one that's, pretty young, but then I'm looking at this other submittal and there's a whole ton of them, but they're 10 years old. Is there a limit to how old these tests can be?
Yeah, so sometimes when you're designing a mix, you're supposed to see how variable, how repeatable the producer is at making it. And theoretically, ACI has this equation that's an over-design factor. And if a producer is extremely repeatable, they need less over-design or less of a safety factor. Hope that makes sense.
Yeah.
And so what they're trying to show you, that we've done this test, we've tested this concrete for 10 years, and for 10 years, we've been getting very, very similar results. Now, if they don't have any recent results, I might be a little nervous. I might ask them why they don't have any recent results. Chances are they probably do, they just didn't share them with you, but they may not. Maybe they haven't used this mix for a while. Who knows? But that's what they're trying to do. They're trying to show you this variability is low so that they can reduce their over-design factor. Now, I'm not so sure that many people really use that over-design factor that much in the field, but theoretically, that's why it's there, and that's what they're trying to do. Hope that makes sense.
Yeah, absolutely. I think that's everything I need. I mean, what a coincidence you knocked on the door.
Happy I could help, and please let me know. And you know what? I've got some YouTube videos online.
Do you?
Yeah, you can find them at youtube.com/Tyler Ley. That's youtube.com/TYLERLEY. I've got about 300 videos on there about all kinds of this stuff, structural engineering stuff, materials engineering stuff. I love concrete. I super duper love concrete. And so that's what I try to do to try to help people, because I don't always stumble across them on, my way to the ACI holiday party. So if you ever have any other questions, maybe you can go there and find them. Let me know.
Perfect. Well, thanks, Tyler. I'm heading to a holiday party now, and you know what? I'm going to put those videos up on the TV, and we'll probably watch them all night and drink hot chocolate.
Let's do it, baby.
All right. Well, thanks so much.
Take care.
You better watch out, you better not cry, better not come, I'm telling you why. Santa Claus is coming to town.
I hear all the good kids are getting concrete this year.